Hello, my name is Joseph Gelfand. I'm a physics professor at NYU Abu Dhabi. On behalf of the NYU Abu Dhabi Institute, I'm very pleased to welcome you to this talk. Today we're going to hear a talk by Professor David Hogg, an engineer who happens to do astronomy. He comes from NYU, but he got his PhD at the California Institute of Technology, where he worked with Roger Blanford and was actually one of the first users of the then new 10-meter Keck telescope, which at the time was by far the largest optical telescope in the world. After he got his PhD at Caltech, he was a postdoc at the Institute of Advanced Studies in Princeton. And in 2001, he joined New York University, and he's currently at the Center for Cosmology and Particle Physics at New York University, where he's been tenured since 2007. So, Professor Hogg.
Thanks very much. Oh, good, we're up. Well, welcome, and thank you for coming out to hear something about dark matter. It's a pleasure to be here. It's been really fun to see NYU Abu Dhabi get off the ground, and there's a lot of success, and a lot of it's due to Yosi and his colleagues at NYU Abu Dhabi who've created a new university here, and it's exciting to see. And it's been fun visiting the department and spending some time here. I'm going to talk about dark matter. So you may know already, but if you don't, here it is. Most of the matter in the universe is not in the form of atoms and molecules and things that you're used to touching and feeling, but most of the matter in the universe is in some form that we don't yet understand. And so I'm going to talk to you about how we know that, and what do we know about it, and what might we know about it in the future. This is an image from the Sloan Digital Sky Survey of a very large number of galaxies. Each of the sort of yellowish blobs you see in this image is a galaxy, and most of those galaxies are actually much larger in mass than our own galaxy. And this image shows a few hundred galaxies. Well, I'll talk more about the numbers of galaxies, but there's a very large number of galaxies we've observed, and we know a lot about galaxies. I was saying we don't know that much about the dark matter, but one of the reasons we know a lot about dark matter is that we know a lot about galaxies. In fact, we live in a galaxy. The galaxy we live in is the Milky Way, and I'll also say something about the Milky Way as we go. So one of the things that's I'm an astronomer. Well, as Yosi mentioned, I'm an engineer. I work on the challenge that the things we care about in the universe are never the things that the data we get are never exactly directly observing the things we care about. So we care about the sort of fundamental causes in the universe. Where did the universe come from, and how is the universe evolving? Our data only sort of indirectly answer these questions. So on this slide, I've got a list of things we know about the universe that you might find strange, and I've ordered them from the most well-established to the least well-established. So the most well-established thing we know about the universe is that it is expanding. This is very well-established. We see it in all observations, and we've known this for quite a while. It was discovered in the 1920s, and we know it because when you look at galaxies around us, you see that they're flying apart, and as you look at further and further galaxies, they're flying apart farther and farther. And there's a whole physical picture for how this works. It's also consistent with our understanding of gravity and the possible origins of the universe. So there's a very, very beautiful model of the universe that is expanding, and it's also very well understood observationally. So now moving down this list, there's more and more strange things. Black holes. So people might think black holes are something that comes from science fiction. This is an object so massive and with such strong gravitational pull, so dense really, that even light can't escape its pull, and so that's why they're called black holes. They absorb everything, including light. It's now very well established that the universe is filled with black holes. We know that there's an enormous black hole at the center of our galaxy, and we know of many other black holes in our galaxy. And they're very well established because, once again, we have very good observations, and we have a theory which underpins them. Then there's I opened this talk by saying the majority of the matter in the universe is in some form that's not atoms and molecules, but some other form. That is now very well established, and that's what I'm going to talk about today. But then there are other things we know about the universe that might be that are less well known, that are more and more speculative, so they're less well established, but are also in this sort of category of strange. So one strange thing about the universe is there's some vacuum energy density to the universe, which is causing the expansion of the universe to accelerate, and that's another component of the universe. I'm not going to talk about that. Another thing I'm not going to talk about is it's now seeming very likely that there are other universes. We have not established this empirically yet, but all of the physical theories we have for the origin of our own universe right now indicate that there are probably, in fact, other universes. And in fact, those other universes are probably qualitatively different from our own. And one of the things that's exciting to me as an astronomer is that you can learn things like this just by looking through telescopes. So when all we do as astronomers is collect photons, we collect light from the universe, and we just get whatever light happens to land in our telescopes. You know, you imagine a star somewhere in the universe, it emits a photon, that photon flies, and by great good luck, that photon happens to be flying towards the Earth, and then it gets towards the Earth, and by great good luck, it happens to be hitting a patch of the Earth where there happens to be a telescope, and by great good luck, that telescope happens to be pointing in the direction that photon's coming from, and by great good luck, the shutter on the camera happened to be open. And it's only those photons that we collect, and yet we learn all of this stuff about the universe from those photons. So I'm going to try and tell you a little bit about that in this talk. Okay, good. So just some reminders. I'm calling these reminders, but don't feel bad if you don't know these yet. So one thing you are supposed to know is that the seasons happen because the Earth orbits a star, which is the sun. That's something you're supposed to know. The relevant time scale, so under that I've written time scale and a length scale. So astronomers and physicists, we think about the world in terms of length and time a lot. So I've given you a time. The time scale for us going around the sun is about a year. It's actually exactly a year, but anyway. And the length scale is about 10 to the 8 kilometers. What is 10 to the 8? It's a 1 with 8 zeros, so it's 100 million kilometers. So the orbit of the Earth is about 100 million kilometers in radius, and it takes a year. And then if you go up the next level, that's the solar system. Now if we go up a level in scale, we get to the galaxy. And our galaxy is called the Milky Way. And the Milky Way galaxy contains tens of billions of stars, maybe 30 billion stars, something like that. And it takes us about 50 million years or 100 million years to orbit the galaxy. And the size of the galaxy is very large. It's 1 billion kilometers in size. It's really, really enormous. Much larger than the solar system. So the solar system is a tiny little speck inside the galaxy. Then going up a scale from the galaxy, you get to the whole universe. And one thing that might be surprising to people in the room, but it's very exciting to me, is the universe is finite in size. It might be in a large sense, it might be infinite. It's possible that the universe is infinite in size in some sense, but the part of the universe we can see is finite. And the reason the part of the universe we can see is finite is that the universe's age is finite, and the speed of light is finite. So we can only see. The universe is 14 billion years old. Actually, the number's known very precisely. I don't remember. It's 13.7 something billion years old. The universe's age is actually known very precisely right now. Because it has finite age, there's also just a finite region we can see. And I find that exciting as an astronomer, because as an astronomer, it means our job is actually finite. It's actually possible for us to observe every galaxy in the universe. That is an achievable goal. And actually I gave a research seminar this afternoon at the department saying that that is one of my goals, is to measure the position of every galaxy inside the universe. The universe, the age, as I said, is 14 billion years, so the time scale is sort of 10 to the 10 years, tens of billions of years, and the size of it is one followed by a lot of zeros, kilometers. It's, I think I translated that to 100,000 billion kilometers. It's not really a number you can imagine, but the important thing is to see that in the same way that the solar system is far, far smaller than the galaxy, it's also the case that the galaxy is far, far smaller than the universe as a whole. There's an enormous range of scales. And of course, I didn't even mention the point that the solar system itself is far, far larger than the Earth, and then the Earth is far, far larger than human beings, and human beings are far, far larger than atoms and molecules. So there's a tremendous range of scales involved in astrophysics. And in fact, in astrophysics, we care about all of those scales. And in fact, I work on projects that touch all of those different scales. Okay, so here's some examples of galaxies. So these are, I'm just going to flash some pretty pictures. It's your job as an astronomer to show some pictures. The universe is ridiculously beautiful, and of course a lot of people work on galaxies because they're beautiful. This is a pair of galaxies which we believe are currently colliding. They're about to crash into each other. This is a very famous galaxy. This is the Whirlpool Galaxy, or M51. This is one of our nearest neighbors, and we know a lot about this galaxy because it's so nearby. This galaxy is not very different from the Milky Way in terms of mass and size. It's a little younger than the Milky Way and a little bit more exciting, and you can see there it's really two galaxies that are also interacting. You can see there's a little galaxy, little yellow galaxy at the top interacting with this galaxy here. And this galaxy has a spiral pattern, and the Milky Way probably, if you could fly out of the Milky Way, which you can't, believe me, you'll never fly out of the Milky Way. But if you could fly out of the Milky Way and look back down on it, it probably also has a spiral pattern like that in its disk. And this is another galaxy that's probably, this is quite similar to the Milky Way in terms of mass. And we're seeing this galaxy edge on, and you can see the disk. There's a very thin disk of stars, and this thin disk here appears dark because the stars are mixed with dust, what really should be called smoke. They're filled with material that's been blown off of stars and supernovae and so on. So there's sort of a dark, absorbing, smoky band where the stars are. And we live in that band in the Milky Way. So when you look in the sky and you see the stars of the Milky Way, and I mean, probably many of you have not seen the Milky Way. Now that we all live in urban centers like Abu Dhabi and New York, we don't really see dark skies. But if you ever get to a really dark sky and you see the Milky Way, it's absolutely beautiful and filled with structure. And most of the structure you see in the Milky Way is actually set by this dust and smoke that's in the disk of the Milky Way, not from the stars themselves. So there was a very important discovery in the 1970s, and there were hints of this discovery long before. But in the 1970s, there was a discovery, and the principal name associated with this discovery is Vera Rubin, who was at that point a graduate student. What she was measuring was these disks of stars in these galaxies, these spiral disks. You can measure how fast the disks rotate. And as I said, the rotation of one of the disks of rotation of these disks of stars takes some 50 million years to rotate, which sounds like a long time to people who live on the Earth. Well, actually, the Earth is much older than that, right? The Earth is billions of years old. So to the Earth, that sounds like a short time. But to you, it sounds like a long time because you're probably not going to live 50 million years. But that spin, though it seems like a very slow rate when you think about 50 million years, in fact, it is too fast. And one of the things that Vera Rubin was doing was she was asking the question, how fast should they rotate if I think they're gravitationally bound objects? In the solar system, for instance, the Earth is orbiting the sun. Actually, it's just as valid to say the sun is orbiting the Earth, but I'm not going to say that because you're not supposed to say that in public. The Earth is orbiting the sun, and the rate at which we orbit is set by the mass of the sun. So similarly, the rate at which the stars go around in this disk is set by the mass of the galaxy. So she was computing the masses of these galaxies by seeing the stars go around, and she was finding the masses were too large, given what she knew about the stars and the dust in the galaxy. So they were spinning too fast, and so she had to ask, what holds them together? And she and many colleagues, this is, every discovery in astronomy, there's no discovery in astronomy that's the work of a single person. Every discovery in astronomy is the work of many people. And she and her colleagues realized that either there must be some additional mass in the universe that they can't see, or we must be wrong about the theory of gravity somehow. There's something wrong with how we're doing this calculation. And the amazing thing to me is they decided way back then that the most likely answer was there's some mass you can't see. And it's a funny decision that they made, because it would have been just as natural to say there's something wrong with the theory of gravity. But somehow astronomers have an intuition about what's simplest, and that was their intuition. And that intuition turned out to be correct, and I'll come to why that is. Whenever I say correct, I mean very probable. Actually, it's an interesting thing about the universe, about astronomy, because, I said at the beginning, everything we know about the universe comes from these photons that happen to hit the telescope. That means we don't get to decide what data we get. The universe decides what data we get. And that means there are a lot of uncertainties in the things that we do. And I was saying, we really know that the universe is expanding. But once you get to dark matter, there are some uncertainties, and I'll bring that back up again. We don't know for sure what the dark matter is doing, and we don't know for sure that we have the law of gravity right. We do know some things about it, though. Okay, good. So this is getting a little technical, but I just want to say a couple of technical things for the science nerds in the audience. The model that was built of dark matter, so what happened in the 70s? So in the 70s, they realized there must be this dark matter. So in the 80s, computers, those of you who are as old as I am, know that in the 80s, computers started to become accessible and started to become standard scientific tools. We had computers. So people said, we need a model of this dark matter that we can simulate on the computer and test whether or not these galaxies really could be made of dark matter, and what would the properties of this dark matter be. So in the 80s, a group of theorists, and I guess a name you would associate with this is Jim Peebles, wrote down a very simple model. In fact, they wrote down the simplest model they could think of for the dark matter, this unseen matter that Vera Rubin and her colleagues had discovered. They said, well, the simplest thing we could possibly assume is that it is cold, which means that it is sort of moving along with everything else in the universe. It's not zooming around in the universe. It's basically at rest with respect to the atoms and molecules in the universe. So they assumed it's at rest. They assumed it's completely non-interacting. It doesn't interact with anything, with atoms, and it doesn't interact with itself except through gravity. It only has gravitational interactions. That's the simplest assumption, because any other assumptions would make the calculations much harder. And then they assumed various things about the initial conditions, which I'm not going to talk about, but which are also very, very simplifying assumptions. And when they wrote down this model, they knew this model must be wrong, because they're choosing this model entirely on the basis of this is easy to calculate. And we don't have a contract with the universe that the universe be easy to calculate. In fact, many of the people in the department here work on pulsars, which is a kind of star that's extremely hard to calculate. And we just spent some time thinking about that. But it turns out this model has explained beautifully an enormous range of observations in cosmology. And we now, at the level now that many of my colleagues consider this model firmly established and undeniable. So this model, which was written down purely as a simplification, has done an amazing job of explaining data. And I'm just going to show you some of the kinds of things it does. So what do we really, well, what does a cosmologist do these days? I am I work in a number of different fields, but in one of my hats, I'm a cosmologist. In fact, I'm in the Center for Cosmology and Particle Physics at NYU, New York. And one of the things we do is we measure, as I mentioned, we're measuring the positions of galaxies. So a lot of cosmology comes from the positions of galaxies. What I'm showing here is a map. This is a map of the positions of a very large number of galaxies. So you might think, what is that like? What is this fiery stuff you see here? That is a myriad of tiny little dots. And every one of those dots is a galaxy quite like our own galaxy. And we live at the center of this. We, of course, are not at the center of the real universe, but we are at the center of the universe we observe. Actually, one of the great things about general relativity is you get to write your own coordinate system. That was Einstein's real contribution to physics was to say that physics is coordinate free. You can decide. You get to decide what the center of the universe is. So in case you were wondering, it's right here. This is the center of the universe, right there. And look, ooh, it just moved. The center of the universe just moved. But anyway, this is a map of the nearest 50,000 or 100,000 galaxies to us. And notice that it's very structured. The galaxies are not uniformly distributed in this volume, but you see how they're collected into clumps and filaments. You see that structure there? That structure, the morphology and the statistics of that structure can be computed in this cold dark matter model, because this cold dark matter model is not just a model for dark matter, but it's a model for how the whole universe evolves. I mentioned something about initial conditions, Gaussian adiabatic initial conditions. That is, the cold dark matter model is a model that's what is the universe like after the Big Bang, and then in evolution to the present day, you evolve it to the present day in a computer, say, and then you can predict what the local universe should look like, and statistically, it looks like this. And so this is our actual universe, but our predictions of the universe match this very well to a few % accuracy. So we live in a universe that is extremely well described by this cold dark matter model. Another image, you may have seen this image before. This image, especially if you're a physics buff, this is the cosmic microwave background. So it's a long story, and I'm not going to explain it in full detail. But if you look out in distance in the universe, I said, the speed of light is finite. So you look out in distance to earlier and earlier. When you look to further and further objects, you're seeing them earlier and earlier in the universe's history. Right? So when I look at galaxies that are very far away, what we find is they're younger than galaxies we see locally. The stars are younger and the galaxies are younger. Why? Because we're seeing them earlier in time, because they're so far away, it took a long time for the light to get to us. If you look to the most distant things you can see, you eventually hit a wall, which is called the cosmic microwave background. This is when you're looking so far back in the universe's history that you get back to when the universe was basically a fireball. The universe was born in this Big Bang. The universe was very hot. It was basically a fireball initially, and then as it cooled, the plasma that was there collapsed into atoms, and then the atoms collapsed into molecules, and the molecules collapsed into stars, and the stars collapsed into galaxies. But it starts off as sort of a fiery, basically it's fire at early times. It's very, very hot plasma. And so we can look back to that original plasma and we can see it. It turns out we can see it. And this is, there were a set of experiments that were done in the 70s. One of them won the Nobel Prize. Penzias and Wilson got the Nobel Prize for discovering the microwave background. And then there was a Nobel Prize in the 90s for measuring the temperature precisely of this radiation, and now we've measured not just the temperature of the radiation, but fluctuations. You see how this has got fluctuations in it? You see this is hot spots and cold spots. And those hot spots and cold spots in this correspond to the initial conditions of the universe. So we know a huge amount about the universe. We know about this large-scale structure. We know about the initial conditions. And so we have very strong constraints on how the universe has evolved. This is like a snapshot of the initial conditions of the universe. Because we can see this snapshot of the universe at early times, which is this cosmic microwave background, and because we can see the structure of galaxies at the present day, that map I showed you of the local universe, because we can see those two times, we can see how the universe evolved. That evolution is driven almost entirely by gravity. The way I would say it is, when we try to explain that evolution, it turns out we can explain it completely just using Einstein's theory of gravity. And Einstein's theory of gravity does a beautiful job of describing that. In fact, even Newton's theory of gravity does a beautiful job of describing it, because Newton's theory of gravity was almost exactly right. Einstein's correction to gravity was actually very slight. And Newton's gravity even is good enough to make this explanation. So we really understand this evolution, not just we can see the evolution, but we can also explain it with our theory of gravity, provided we add dark matter, cold dark matter, this dark matter we needed to explain the galaxies. In the solar system, so you may know that we can measure the positions of objects in the solar system very precisely, and extremely precisely. Like, we know the position of Mars right now to a centimeter. And Mars is 10 to the 9 kilometers away, and we know it's a billion kilometers away, and we know its position to a centimeter. And the reason for that is we can make very precise measurements in the solar system. In fact, we can do radar in the solar system, where we actually bounce light or radio signals off of the planets. And then we have this very precise theory of gravity, Einstein's theory of gravity. And when we compare the observations we make of the solar system to our theoretical predictions of the solar system, they match beautifully. In fact, they match to 13 decimal places in accuracy. That means we can predict the position of Mars to a centimeter, and we can measure it to a centimeter, and the prediction and the measurement agree. See what I'm saying? That's a little different from things you're used to. You know, like you walk around the supermarket and you put things in your cart and you're kind of adding it up, and you get up to the front and you say, well, I think this will be about 40 bucks. And it's 38. And you're like, yes. This is kind of different from that. And then there are laboratory tests, so you can test gravity in the laboratory too, and so you can bring large masses together in the laboratory and measure the forces between them. Turns out that's a very hard thing to do, but there are a few people who are very, very good at this. And at all of these scales, from the laboratory to the solar system to the universe as a whole, we have very, very precise tests of our gravitational theory. So the theory of gravity is just one of the most beautiful and well-tested things in all of physics. Technically, it's not the most well-tested theory in physics. There's an even better tested theory, but it's pretty darn good. And so this gets at this question. So in the 1970s, when they saw this discrepancy between the rate at which galaxies are orbiting and the mass they thought should be there, and they said, what's wrong? Have we got the theory of gravity wrong, or have we got the amount of matter wrong? And they said, it's probably the matter. Well, once again, they turned out to be right, because our theory of gravity is extremely well tested. The laboratory tests go down to less than a millimeter. The law of gravity has been tested on scales that are 1/10 of a millimeter, meaning they bring two tiny little masses together 1/10 of a millimeter apart. That's actually not quite how they do it. They do it with torsional pendula, and they bring masses very, very close to the surface of a pendulum. They look for deviations of the pendulum's behavior due to gravitational forces. But the law of gravity has been confirmed to follow the Einstein prediction as small as 1/10 of a millimeter and as large as the scale of the whole universe. And as I mentioned, at the solar system scale, it's tested with 13 digits of accuracy of precision. So this is one pretty darn good law of physics. And despite that, there are people in the physics community who are looking for new theories of gravity. In fact, one of them's in the room here. And these, because there is a hope that despite this great success of the theory of gravity, that new things can be discovered in the gravitational sector. People would really like that to be true. For instance, you've probably heard of string theory. There's a hope that if you get to really small scales, smaller than that scale, you will start to see deviations from the law of gravity. But right now, there's no empirical evidence for any problems with the theory of gravity. It's just a beautiful theory and extremely well tested. And a lot of what we do, actually it's funny, a lot of what we do as cosmologists is futile testing of theories. You know, if you set out to test the theory of gravity, you know it's going to pass the test. If it fails the test, you'll become extremely famous because you'll be the person who broke gravity, which would be an enormous badge of honor to have broken gravity. You might get the Nobel Prize for breaking gravity. But you know when you do these tests that gravity's going to win, and it's always won. It's been really an impressive period in physics as we've learned this level of precision. Okay, good. So that was supposed to say, it really is, there's a problem with the universe. We need this extra mass. It is not because we were wrong about the theory of gravity. There really is extra mass. What is that mass? What is it? Now, a lot of people ask me in talks like this, well, could it be this? Could it be that? Could it be this? Like, could it be rocks? Could it be planets? Could it be dust? Could it be dead skin cells? I was once asked whether it could be love. That would be cool. But it might be love, but it makes no testable predictions, that theory. Why? We know it is not rocks. It is not smoke or dust or dead skin cells. The reason we know it's none of those things, why do I say dead skin cells? Because most of the dust in your house is dead skin cells, sorry. But anyway, because astronomers talk about dust. I said that galaxy disk is filled with dust. It's not like the dust in your house. The dust in your house is dead skin cells. The universe is not filled with dead skin cells. But the reason it can't be any of those things is those things are made of atoms and molecules. And if the dark matter was made of atoms and molecules like this, what happens to this? You see, you can see this. Therefore, it's not dark matter. Light reflects off of it. Light is refracted by it. This is a lens. You can use the light is refracted by it, reflects off it, absorbed by it. Light interacts with this in lots of different ways. Even the most transparent piece of glass you could ever make refracts light and reflects light and absorbs light in ways that we would easily detect with the dark matter. The dark matter really is extremely non-interacting. It does not interact with light at all. That's the sense in which it's dark. It's not dark like painted black. It's dark. Dark is actually a bad name for it. It shouldn't be called dark matter. It should be called non-interacting matter. It does not interact. And so what are the options? It has to be an exotic particle. It cannot be anything like ordinary stuff. It has to be something completely exotic. And there are lots of ideas out there for what it might be. And in fact, there's a whole industry, a theoretical physics industry, of coming up with ideas. And the most responsible of those theorists also make predictions. Some of those ideas make predictions. So let me just say a few words about some of the ideas. So there's only one idea about dark matter that is simply motivated in our current physical model, like the standard model of particle physics. There's only one sort of well-motivated idea, and that is something called weakly interacting massive particles, or WIMPs. So you might, and there's a long story about the WIMP and why it has that name and so on, but weak is actually a technical term in physics. You may know that there are 4 fundamental forces in physics. That might ring a bell from high school. There are 4 fundamental forces, and one of them is the weak nuclear force. In fact, we now think all forces are in fact unified, and there's only really different manifestations of one kind of force and so on. But in the classic classification, there's 4 kinds of forces, and one of them is the weak nuclear force. And the weak nuclear force is responsible for neutrinos, which are not particles you encounter every day. And one of the reasons you don't encounter neutrinos every day is they're very weakly interacting. So the sun is spewing out neutrinos all the time. There's billions of neutrinos passing through your hand every second. This whole room is just flooded with neutrinos. Those neutrinos pass all the way through the Earth, and the Earth is completely transparent to neutrinos. And so they are very weakly interacting, like in the traditional sense of the word weakly interacting, and they are technically weakly interacting. They interact via the weak nuclear force. And it is possible for the dark matter to be like neutrinos in a certain sense, in the sense of interacting in the by weak nuclear forces and nothing else. So there's a motivated idea there, and you may have heard of the Large Hadron Collider in CERN, which has just discovered the Higgs particle, which got the Nobel Prize this year. One of the motivations for building the Large Hadron Collider is it might be able to discover these WIMPs. If these WIMPs exist, and they couple to normal matter using the weak nuclear force, it's possible that the Large Hadron Collider will discover these WIMPs. So this is a very exciting possibility. In fact, one of the reasons we love this model is it makes a testable prediction that eventually you will see these objects in an accelerator experiment. Then there are much more exotic particle ideas that aren't as well motivated but are fun to think about, and many of them don't make many predictions. Here's a crazy one. So axions, which I mentioned there, have some crazy properties. One of the crazy properties of axions is that in principle, if you shine a really bright light in the room over there, you'll see it come through the wall, because some of the light will turn into axions. Axions can pass through the wall and then turn back into light once they get in here. So axions are really strange particles that can do things like that, and a lot of their properties are ruled out by experiments. You can see that's an experimental prediction. It's been tested. There was literally an experiment in which they had a big wall at Fermilab and shot a laser at the wall and had a photo detector here seeing if they could see the laser come through the wall, and it didn't. Duh. I mean, if you describe that experiment to your mom, like, hey mom, we're doing this experiment. I don't know what she thinks about that, but anyway. So there's a lot of really exotic particle ideas that are, but it's nice when, that was a very good example, because that was an example that actually made a prediction that people could test. And we love it in physics. If you make a prediction, we can test. Another possibility is that the dark matter could be black holes. So I told you, we know that black holes do exist in the universe. We've seen observational evidence for large black holes, very large black holes. And we know that the dark matter is not very large black holes, but the dark matter could be tiny black holes. And that's a great idea, but one of the problems with that theory is it does not make much in the way of predictions, and so it's a very hard theory to test. And then, as I said, importantly, it cannot be dust or rocks or molecules or planets or comets or any of those things. It cannot be anything that's made of normal stuff. That's very strongly ruled out now. Good. So I mentioned that some of our theories of dark matter make predictions. And for that reason, there's a lot of people searching for dark matter in different ways. I said we hope that the LHC might directly produce dark matter. That hasn't happened yet. And in fact, a lot of hopeful ideas about dark matter are now ruled out by what the LHC has already done. That's Large Hadron Collider. There are other hopes. One kind of thing people do, and some people here at NYU Abu Dhabi do, is try to directly detect the dark matter that once in a while passes through this room. So, I said that this room is flooded with neutrinos all the time. Why is it flooded with neutrinos all the time? Because the sun is out there blowing neutrinos at us, lots of neutrinos. Now, the dark matter locally is not very dense. There isn't that much dark matter in the room. But occasionally, dark matter particles do come through the room. And it depends how many there are in the room, depends on the mass of the dark matter particle, and so on. There's a lot of uncertainties there. But there is dark matter in most of these models. Dark matter would be passing through the room every so often. So the hope is, if it is a weakly interacting particle, maybe occasionally it interacts with something, and we could see that interaction. Just like the neutrinos coming through the room occasionally interact with something. Occasionally one of them scintillates in this water and emits a photon. You would never notice because the room's really bright and filled with photons. But if this was a very dark room, instrumented completely with phototubes, and there was no other photons in the room, and this water bottle was the size of the entire room, then once a day or so, you'd get a photon from one of the neutrinos coming through the room. And so similarly, such things might happen with the dark matter particle. And so people here and all over the world are building detectors such that if they interact weakly, we will see occasionally a signal. And right now, there are no convincing detections. There are some tantalizing hints. Some of the experiments are showing some signals. But right now, it looks like those signals are all background noise that is being accounted for when people try to understand the confusing signals. Another possibility is annihilation. So if you have an electron and you have a positron, when they find each other, they annihilate. So for every particle, there's an antiparticle. And when the particle and the antiparticle interact, they disappear and then create some burst of radiation. In the case of an electron and an anti-electron, which is called a positron, an electron and anti-electron, they produce photons. They produce light when they annihilate. In the case of dark matter, it's possible that the dark matter particle and the antiparticle exist in the universe, and it's possible that sometimes a dark matter particle and a dark matter antiparticle would find each other, and then they would emit a burst of some kind of radiation. And there's been a lot of work done to ask, can we detect that radiation? And once again, there are some tantalizing hints, but there is no clear signal of dark matter annihilation. I would love the dark matter to be annihilating, because then it would be astronomy again. The dark matter would be emitting photons, which we could observe with telescopes, which is what I do. One of the interesting things about these experiments is they're not expensive. It's very inexpensive to search for dark matter. The Large Hadron Collider, that's expensive. That's a very expensive machine. But the kinds of laboratory experiments that might directly detect dark matter in the lab are actually not that expensive. It's a place where, in principle, somebody might make a huge impact on physics with a very small scale experiment. There aren't that many opportunities as physics has become very industrial as a. Okay, good. So I want to say one last thing about the dark matter, which is I, of course, am working on what is the dark matter, and I'm an astronomer. I'm not trying to directly detect it. I'm not trying to produce it at the LHC. I'm trying to observe it. And observing it is very hard because it doesn't interact with anything. And in particular, it doesn't interact with light, and I have only light to work on. I have telescopes that collect photons. That's all I do. But there's an interesting prediction. So that little postage stamp there, that little black box, has a picture of a little galaxy in it. That galaxy is probably not unlike our own galaxy. That's not our own galaxy, because of course we don't get to see our own galaxy from that direction. That's somebody else's galaxy. But it's similar to our galaxy. And I've pasted it on top of a simulation of dark matter. So all this pink, yellow stuff you see there is from a simulation, a computer simulation of what the dark matter for that galaxy would look like. Okay? So several things that are very, from my point of view as an observer, thinking about how to detect the dark matter and how to understand it, several things very important about this figure. One is, the galaxy is tiny, but the dark matter distribution around the galaxy is huge. If this is our galaxy, if our galaxy is this big, the dark matter goes way out to here. The dark matter is much, much bigger. It's not just that there's more dark matter than stars. It's that the dark matter extends out to very large distance. And that's part of the theory of dark matter, but it's also very well established now experimentally. We know that because of by looking at the orbits of stars, we can see that. We can see that even the stars that are very large distance are being affected by the dark matter. And we also know that from gravitational lensing, which I'm not going to talk about, but we know that the dark matter does extend out like that. But there's another interesting thing about all this dark matter, and that is the distribution of dark matter is not smooth. The distribution of dark matter is filled with clumps. You see all these purple and yellow clumps. Those are clumps of dark matter within the dark matter. So the dark matter is almost like a fractal. Like there's a blob of dark matter, and within that blob of dark matter, there are blobs of dark matter. And within those blobs of dark matter, there are blobs of dark matter. It's very clustered and featured. And that is one of the things, that's one of the places where we hope to be able to learn more about the dark matter. The fact that it's not smoothly distributed is going to have an impact on our observations. And this is the kind of observation that I'm very excited about now, and is getting better as time goes on. This is an image of the sky. This is a real image. This was taken by a colleague of mine named David Martinez Delgado. And this is an edge-on nearby galaxy, and we're seeing it edge on. By luck, we see it edge on. And he took this is a very long exposure. I think the exposure time is 2 weeks. He had the shutter open in his camera for 2 weeks. Okay, this is not an easy observation to do. He had to devote a telescope to this project continuously and to get 2 full weeks of observing time on a galaxy, you have to observe for months, because sometimes you get bad weather, sometimes the sun is up, sometimes there are clouds or rain, or sometimes there's windstorms and sandstorms. Well, you guys know all about sandstorms, but it's really a very hard observation. But when he does this very deep observation, what does he see? There's not just the galaxy here, but do you see how there's like a big loopy ring of stars around this galaxy? So that loopy ring of stars is a very valuable thing, because that is a set of stars that's orbiting around the galaxy. And what's it doing? It's passing through this dark matter halo. This dark matter, this huge distribution of dark matter that extends out to large distance and is filled with lumps. And those lumps affect the orbit of this stream of stars. And so one of the things I do in my work is try to think of ways we might see the detailed properties of the dark matter. Given that we can never detect it directly, we can't see the photon, no photons are coming from the dark matter, no photons are bouncing off the dark matter. How can we observe it? The only ways we can observe it are dynamically. We look at systems like this, where there's a dynamical system that is interacting gravitationally with the dark matter, and that's what we look at. Okay, that is my last slide, so I'm just going to pull back to my first statement here, which is the things we know about the universe. And I just want to make just a final comment that in astronomy, as I keep mentioning, all we do is see photons. We just get light. But of course, what we're interested in are we're interested in the origin of the universe and the causes of the universe. What we want to know as scientists is what made the universe and what gives the universe its properties. Those are causal questions about how things have changed and evolved, and how they started and how they've evolved and how they've changed. And those questions are always indirect questions. All we get to do is take data and try to explain those data. And there are some things that, despite these limitations, that all we get is the data that happens to fall into the telescope, there's some things we know really confidently. We know the universe is expanding really confidently, and we know that there are black holes. And the amazing thing to me, and that if I wanted you to remember one thing from this talk, it would be that the fact that the universe is dominated by this dark matter, that unseen matter controls the evolution of the universe and determines the properties of the galaxies we live in, that is now an extremely well-established fact, even though we know almost nothing about what that dark matter is. Thank you.
Secretary, Professor of Physics, Theoretical Physics. Let's go back to dark energy. As we know, dark energy is the energy of the vacuum, and it is the cosmological constant.
Yes.
And a lot of people worked in theoretical calculation of cosmological constant based on quantum chromodynamics fluctuations. And also the cosmological constant measured experimentally. And there's a 60 order of magnitude between experimental result and theoretical calculation.
Good.
I know this is one of the major unsolved problem of physics.
Yeah,
But
good.
did you just give a notes about this, your opinion about this point?
Okay, good. So the point that was just raised is, I mentioned there's this dark energy that we now know the universe is, it's not just expanding, but the universe is accelerating its expansion. And we believe, but there's a sort of concept of this dark energy, that the vacuum, even empty space, contains some kind of stress energy tensor, some kind of non-trivial properties. It's not just empty. It has dynamical properties, even the vacuum. When people try to compute how big this effect should be, they find in the computation that it should be so enormous that it would have ended the whole universe in a tiny fraction of a second, and we'd be gone, like nothing would ever form. So there, and as you mentioned, this is one of the biggest problems in fundamental physics. I didn't want to imply in my talk that we understand everything in physics. In fact, there's quite a few things that are completely not understood right now. And the fundamental theory of particle physics seems to predict that there should be this enormous vacuum energy density, and we find this tiny, tiny vacuum energy density. And so that's why I wouldn't there's kind of a line between dark matter and dark energy. Above that line are things we kind of understand, where we have observations and we have a theory and things fit together. But below that line, I wouldn't say that. We don't have a theory for this dark energy at all. And I don't really have anything to say about it, except that I accept an intuition that that's one of the things that I think motivates people to look for modifications to gravity, because the only idea I've seen in seminars that I'm happy with for getting rid of all those orders of magnitude is to have somehow gravity not be sensitive to this sort of zero level term that's there, this sort of degravitation idea. So I don't know, but I don't know. I have to say, physics is filled with outrageous unsolved problems, and there's a lot of opportunities for people to revolutionize the way we think about even ordinary things like empty space. It's amazing. Empty space is not understood. We understand a huge amount about atoms, we understand a huge amount about molecules, we understand a huge amount about neutron stars, but we don't understand empty space. And that's that's a very, very good comment, and it's worth keeping in mind that while there are these things we understand very deeply, there are things that are very, very confusing.
By the way, empty space it is very complicated medium. It is a lot of quantum chromodynamic fluctuation.
Exactly. It's
a Nobel Prize laureate David Gross. He did the calculation.
Exactly.
And he got Nobel Prize 2004 about calculation elementary particle about asymptotic freedom. He did such calculation to calculate the quantum chromodynamic fluctuation of the empty space, of the void, vacuum, empty vacuum.
Yeah. No. In fact, yeah, it's a very good point. In our current understanding of quantum mechanics, which is sort of the underpinning for all of our theories of particle physics, the vacuum is not a boring place. Lots of things are happening in empty space, and it's a very interesting and totally unsolved issue.
I have two questions.
Yes.
Is there any theory which says that our universe is part of another universe?
Good.
Second
Yeah,
question.
good. Yeah.
Let's assume that our universe is part of another universe with our technology we have now.
Would we find it?
Can we say? Can we find out whether it is?
Okay, so I can give you an answer to that, which you might not find very satisfying. So one of the interesting things that's happening in theoretical physics right now is there's a lot of interesting ideas that happen. So we live in a three-dimensional space here, and then we have time as a kind of fourth dimension. So physicists will describe our world as 3 + 1 dimensional. We have 3 dimensions which we can move around in, and we have one time that we move forward in, I guess. And that's all we've got. Now, mathematically, you can think about higher dimensional objects. So mathematically, you can think about 5 + 1 dimensional, or 5 + 2 dimensional, 2 times. And people think about models that have much more dimensions. So it's turned out to be a very productive thing in physics, in theoretical physics, to think about the possibility that we live in 3 + 1 dimensions that's somehow embedded in a larger space. So you might have heard that in string theory, there's 26 dimensions. Or there's sort of 10-dimensional and 11-dimensional theories. So there's a bunch of theories of fundamental physics. These are attempts to unify the laws of physics. Remember, I said that the laws of physics are all now unified, or the forces are all unified. One of the attempts to unify the forces involves increasing greatly the number of dimensions. And then we somehow live in a subspace of that higher dimensional space. In that sense, if those theories are true, then it really is kind of true that our universe is embedded in a larger universe. And you might say, well, that's crazy, and it's fine to say it's crazy because it is crazy. But these theories are being worked on because they might help solve some anomalies. In fact, one of the anomalies that these theories are designed to solve is this vacuum energy density theory, this vacuum energy density problem, that there's these wrong vacuum energy densities. And so they do make some predictions for the universe on very large scales if we are embedded in a larger, right now none of them have been confirmed, and it's way too early to tell. But it is actually an idea that people take seriously, that we might be embedded in a larger universe, and that might be discovered using cosmological observations within the next decade or so. That's a great question.
It may be a naive one, the first one. Is our universe finite in extent, or is it only the part that we can see?
Good, that's a great question.
Okay, and then the other question, you mentioned that there is a theory that's even more better proven than gravity. Which theory is that?
Good. Okay, great. 2 good questions. On the first one, how big? Obviously, as I said, the part of the universe we can see is only 13.7 billion years in size, but that's really because of the age of the universe. And so the universe could, in principle, be much larger than that, but that's just all we can see. So right now, we cannot say very much definitively about how big the universe really is. we do know, well, no, it seems very likely that the universe is much larger than the bubble that we can see. You can think of what we see as a bubble, because it's a sphere, basically, that we can see. And the reason we think the universe must be substantially bigger than this bubble is that we don't see any sign of an edge. The universe over here looks the same as the universe over here and looks the same as the universe over here. We don't see any sign that we're like coming to the end of the universe in any direction. And that uniformity, the fact that everything in this bubble looks very similar, strongly suggests that if there is an edge, it's very far away from our bubble. So some people think that probably means it's infinite. There are some theoretical reasons to believe it kind of has to be finite, but they're very theoretical reasons. But anyway, we do think it is much larger than the bubble we currently see. That's the current belief. Actually, one of the things that people work on is to look for the possibility that there is an edge, some edge or appearing just visible in the universe, and there's no convincing evidence of an edge. A lot of people are thinking about this question of if there was an edge, would you see it and how would you see it? And there's no evidence of it at all. Maybe you would dispute that. No dispute. The other thing I would say, the other question was, what's the theory that's more tested than gravity? There is a theory that the theory of the interaction of electrons and photons is QED, quantum electrodynamics. So it's about how electrons and photons interact, and it is a very simple theory and can be calculated extremely precisely, and it can also be measured extremely precisely because we're so good at manipulating electrons and light. So there have been very sensitive experiments to measure the interactions of photons and electrons. And those experiments now make predictions, confirm predictions at 15 or 18 decimal places, very large numbers of decimal places. And that theory is extremely well tested because we get to manipulate it in the lab. And I don't get to manipulate gravity in the solar system. We do a little bit because we get to throw satellites out there. But for the really strong tests of gravity are really coming from the solar system as a whole, and we didn't get to set up that experiment. If we had been allowed to set up that experiment, we could have done a better job of testing gravity. The universe did not design the solar system as the best possible gravity testing system it could have. There's some changes I would request if I wanted to test it. And people are thinking about launching satellites that would test gravity, that would take non-trivial paths through the solar system such that they would test gravity more precisely than we know it yet. But for now, the laboratory physicists beat us.
Yes, good evening. How does the universe end?
Good question. I'm getting such good questions. The question was, how does the universe end? Which is a great question. So a couple of things. Let me make one point, a piece of philosophy. So one philosophical point I would say is astronomers study the past. I only ever get to see the past because I'm studying very distant things, and it took a long time for the photons to get to me. So I only ever get to see the past. Now, we're scientists, so we make predictions. So we could ask, what things can we predict? And the predictions that have been successful in astronomy are not exactly predictions of the future. They're predictions of new data we could take. So we observe a neutron star doing something over here. So we say, oh, the neutron stars over there ought to do such and such else because this one's doing this. And then we go and look at them and they're doing something else. But in fact, that's a prediction about a past thing because we're observing that in the past too. So astronomers really only study the past. We're like historians. Right? So we don't really study the future. So that's one point of philosophy. Another point of philosophy is that the universe goes through different phases. So if you, as I said, if you go back far enough in time, the universe was filled with plasma. It was like a fireball. Now imagine we were observing that universe. Imagine we lived in that universe. First of all, it'd be really hot. But imagine we evolved like spacesuits so we could live in this plasma hot fireball. We lived in a fireball. We would look at the universe and we'd look at its past and we'd like, not only is it a fireball now, it was even hotter in the past. This is like the crazy, we live in this fire universe and it will be fire forever. And then one day, foomp, the fire essentially went out. The molecules, the plasma collapsed into atoms, and then the atoms collapsed into molecules and stars formed and so on. But if astronomers had lived back in that fireball phase, they would never have predicted that there would be stars. They probably wouldn't even have predicted that there would be atoms, let alone molecules, let alone stars. So they would have done, the astronomers back then would have done a very bad job of predicting our current universe. If they thought, what's it going to be like in a few billion years? You know, the universe, it was a fireball for a long time, by the way. It was a fireball for 300,000 years. So they had a lot of time to think about it. So in those 300,000 years, all the scholars who are working on the astronomy in this fireball universe would be writing papers. What's the universe going to be like in a billion years? Will the universe even live for a billion years? They would never have predicted stars and galaxies and so on. So that's another kind of philosophical point. We're not going to do a good job predicting the future. If you believe, however, that the universe contains only the things we currently know about and nothing else, which is a bad assumption. That assumption's been wrong at every previous time in history. But let's assume that right now we know everything that's in the universe, and assume that all of the physics is also known. The standard model of particle physics is exactly correct. And the dark matter is truly a non-interacting dark matter, and the dark energy is purely a vacuum energy density. If we assume all of those things, then what happens in the long run is, so there's three competing effects. One effect is there are black holes in the universe that are swallowing up everything that comes near them. Now, they don't do that very fast. There's a huge black hole in the center of our galaxy, and our galaxy's been around for billions of years, and it's got hundreds of billions of years to go. Like, you don't have to, like, worry. You don't have to, like, call your loved ones because there's a black hole in the center of the galaxy. You got plenty of time. But the black hole, but the black holes do always grow. They always grow. They keep on growing, and they're just taking in more and more material. So black holes are grabbing stuff. Another competing thing is nuclear reactions take everything to iron. Nuclei bigger than iron tend to fission, and nuclei smaller than iron tend to fuse, and everything heads towards iron. So my wife loves that. She loves the idea that the universe will be iron, because she's imagining it's like a skillet. Like clang, there's your universe. So that's the next competing thing. And then the next competing thing is that we believe that the proton that nuclei, even though iron is very stable, eventually it must decay into photons. People believe that the nuclei must decay into photons for very fundamental particle physics reasons. It ought to decay. Now, there are very strong limits on that decay, and it might be that it doesn't decay and something protects it from decay. But we don't know how long that decay takes because we've never observed it. We don't know how long it's going to take, and we've never observed one. So we don't know of these three effects in what order they will happen and how things will go down. And it depends on some competition of those effects. But one thing seems very likely, so we don't really know. My answer is, I give you three answers. We shouldn't want to know because we're astronomers. We can't know because you can't predict the future. And even if you assume that everything we know is correct, we still don't know because there's some competition between this proton decay and the conversion to iron and the collapse into the black holes. But suffice it to say, one thing that is certainly true is the universe is going to get much more boring. The universe just gets steadily more boring with time. And the reason is, not only are we expanding, we're expanding, right? So all of our neighbors are getting further apart. So it's getting harder and harder to observe other galaxies. They're getting farther away. That expansion is accelerating, so they're actually getting farther away faster. So in another few billion years, all the galaxies in the universe are going to be fainter. But in addition, stars are burning out. In 5 billion years, our sun will die. 5 billion, still plenty of time. But in 5 billion years, the sun will die and other stars are dying. And so the universe is also getting dimmer. The stars are dying, the galaxy will get dimmer. There's less and less gas to form into new stars. So the galaxy will get fainter and the other galaxies will get further and further apart. Fewer and fewer stars will be observable. And basically, people will stop doing astronomy. In 6 or 7 billion years, no one will want to do astronomy. I mean, we'll all be, the Earth will be gone, various stars will be gone, but if there's still intelligent civilization, astronomy, it'll be so boring. So the one thing I'll give you is that the universe will be a lot more boring in the future.
Can you go back to the concepts of finite and infinity and just talk from your scientific perspective a little bit about how they can be separate? If something is to be believed finite and it implies an edge, is there something on the other side of that edge?
Good, good, good. You say that's a quick question? That is a good question. So one really interesting thing about so the universe is expanding. Let me answer a different question first. So the universe is expanding. So a lot of people ask, what's it expanding into? That's one kind of thing people ask. And another thing people ask is, if it's expanding out from where? Like, where's the center? If it's expanding, where's that center? So these are two kind of very generic questions you'd ask if you lived in an expanding universe, which we do. One thing you would ask is, what's it expanding into? And the other is, where is it expanding from? And one of the really, really weird things about geometry is that you actually don't need, neither of those questions has to have an answer. It might be that there's just no answer to those questions. They don't have to have answers. Not all questions you can write down as grammatically correct questions have answers. So one example that people sometimes give, this is a misleading example. I'm embarrassed to even give this example because there's a lot of misleading things about it. But imagine you had a balloon. Imagine you had a balloon and there's ants crawling around on the surface of the balloon. Okay, so I have a balloon here. There's ants crawling around on it. It's kind of gross. Okay, now I inflate the balloon. So I blow up the balloon, and so the balloon gets bigger and bigger and bigger. Right? The ants notice that they're receding from each other. You see how the ants would see that their nearby ants are all moving away? And every ant would see the ants around it moving away from it. And so every ant would say, well, I'm an expanding universe, and they'd ask, where's the center? Which ant is at the center? They would be all calling each other on their mobile phones saying, have you noticed that it's expanding, that space is expanding? They'd be like, yeah, where's it expanding from? And one of them would say, well, I'm the center of the universe, clearly, because everything's expanding away from me. And another one would go, no, I'm the center of the universe, because I look at the ants around me, and they're all expanding away from me. And you see how all the ants would see all the ants around them as expanding away from them? But none of them would be at the center. So the question of so this is not answering, but notice I'm not answering your question. But it's somehow relevant. It's somehow relevant that the fact that it's expanding does not necessarily mean there's a center. And the thing that I don't like about the example I just gave is it implies that it's expanding into something, but it doesn't have to be expanding into something. It can be just that space itself is described itself by the universe. Like there might not be any there outside there. You know, like there doesn't have to be, there can just be the universe and that's it, and it happens to be expanding. Now, the reason I bring that up when I'm trying to answer your question is the question of what is finite and where's the edge, what would the edge of the universe look like and how would you see that it was finite or whatever, is somehow in the same category as those questions, in the sense that it isn't obvious. There might not even be an answer to the question of is the universe finite in extent. We do know the universe is much, well, not know, but it seems very likely, as I said earlier, that the universe is much larger than the bubble we see. But there might not be an actual difference between saying that's large but finite and it's infinitely large. Those might not be different cases somehow, because that question might come into the same category as this question of is there a center and what's it expanding into? It might be in that category. So I'm not saying that specifically. I'm just saying that some of these questions about finite and edges and so on don't necessarily have answers. Now, there is a sense, though, that in the sort of standard models people have, so now I'm going to get serious and try to answer your question. In the kinds of models people have proposed for how the universe emerges from whatever is before the universe, whatever you would call that, the pre-universe thing, the edge really would be a very visible object. In fact, the edge would probably have radiation properties. So it would either be like pitch black, or it would be glowing brightly in gamma rays, or something like that. It would have it would look different from our universe, the edge. So when we're asking the observational question of like, is there an edge? We're asking, do we see any changes to the radiation properties of the universe or the thermal properties of the universe or something like that? And then the question of whether it's finite or infinite, that is kind of, now you're getting to a very theoretical question, because large and finite and infinite don't actually make different predictions for what we actually observe. And so that's why I was sort of pushing you off in the direction of, I don't have to answer all questions. But you know, I think in present day physics, people are very afraid of infinities. And there aren't many infinities in physics. And in physics, we're trying very hard to get rid of infinity. People don't like infinity. It shouldn't be there. Everything should be finite. And so I think that's one of the reasons why, I mean, in physical theories, when something produces an infinity, if you get a result, you do some integral, or you do some measurement, you do some theoretical prediction, you get infinity. People usually think there's probably something wrong with that theory. And so from a sort of theoretical approach, we're very, very biased towards the idea that the universe would be finite, large but finite. But how is that for a non-answer?